Okay, starting off in chapter 3 here, section 3.1, we're going to be talking about functions. And this is really, this first chapter, especially these first couple of sections, are really critical because we're going to spend most of our semester talking about functions. We're going to start in chapter 3, just kind of setting up functions and defining those and looking at some basic properties of functions. And then as we move into chapters 5 and 6, which will be where we look next, we're just going to continue looking at different types of functions and different properties with those functions. And so it's really crucial, really important that you understand the material here in these first couple three sections, especially when we talk about the domain of a function. And there's some questions we're going to ask this first chapter that we're going to continue to ask as we move through the semester. And so can't stress enough how important these first few concepts are. So we're going to start here in 3.1, just defining what functions are, and then looking at finding the value of a function, the domain of a function, and then look at the sum, difference, product, and quotient of two functions. And so this is just kind of laying some, like I said, some groundwork for the rest of the semester. So first, let's figure out what a function is. So before we can talk about functions, we need to talk about what are called relations. Relations are pretty simple. It says, when we're dealing with algebra in real-world situations, we often are interested in the relationship between two variables. When the value of one variable is related to the value of another variable, we have what's called a relation. And so just an easy example of that, if we were to look at maybe a relationship between engine size and gas mileage, we could ask the question, is there a relationship between those two variables, the size of your engine and your gas mileage? And most people would probably say, well, yeah, definitely there's a relationship there. Typically, the larger your engine is, the lower your gas mileage is. And we could, to kind of see that relationship, maybe we could look at some different engine sizes. And let me write that a little neater. Let's do that again. So maybe 260 has gas mileage of 25, and as these numbers get larger, we would see probably that gas mileage is going to drop. And just so we know which goes with which, we could draw arrows across here. Okay, so an engine size of 351 cubic inches might get 15 miles per gallon. Okay, so we could say there's a relationship here between engine size and gas mileage. And that's just a relation. And that's something it's a pretty simple idea to talk about a relationship between two different variables. We could name a lot of different examples of that. So just kind of fleshing that idea out a little bit more. In math terms, we say that a relation is a correspondence between two sets. And typically we refer to those sets as like x values and y values. Those are the kind of the standard variables we use when we start talking about relations and functions. So we could say that if x and y are two elements in the sets and there's a relationship between x and y, we could say that by saying x corresponds to y, or we could say y depends on x. Again, going back to our engine sizes and gas mileages, we would say that maybe this is our x variable, gas mileage is our y variable, and we could say that x corresponds to y. In other words, engine size corresponds to gas mileage. That would make sense. We could also say y depends on x. In other words, gas mileage depends on your engine size. And again, if we think about that does make sense to say that your gas mileage would depend on your engine size. Okay, and so x and y, again, those are typically the two variables we use. We also could speak in terms of input and output. So going back here again to this example, we could say that x is our input, y is our output. And so for some engine size and gas mileage, this engine size could be considered like an input variable, and then the gas mileage would be an output variable. That makes a lot more sense when you actually start dealing with functions and relations as equations with x's and y's, which we'll see that in just a minute. You could also put some other words up here. We say that this is our independent variable. These are some words you'll see sometimes. And this is our dependent variable. So remember earlier I said y depends on x. Your gas mileage depends on your engine size. So that's why this is our dependent variable. This would be our independent variable. And those always typically correspond with x and y. X is independent, y is dependent. There's two more words we could throw in there as well, which we'll get to here in a minute. But just for the purpose of making this this list here, I'm going to put two more words up here. Those are domain and range. And we'll define those here in just a little bit, but just to go ahead and kind of get those associations set up. Domain, again, goes with our x variable. Range goes with our y variable. We'll talk about domain and range here in just a minute. But these are all words you need to be familiar with. Input, independent domain, output, dependent range. And just know these go with x and these go with y. So when we start talking about these relations, we could show that relationship in several ways. Maybe to show that relationship between x and y, we could look at an equation. Y equals 3x minus 1 as an example. And so, you know, maybe in this relationship, you can take your x value, maybe it's 0, multiply it by 3 and subtract 1 and get a y value, -1. Okay. So maybe that equation describes that relationship between the two variables. Well, if you've got an equation, can you also graph that? You know, we could just quickly sketch a graph. You know, 3x minus 1 might look something like this. So we could definitely also graph that equation, and then that line represents that relationship between x and y. Remember, this is your x-axis and your y-axis. Okay. And well, if you've got a graph, think of what you know about graphs here. Don't you also have some ordered pairs, some points along that line there? Well, all of those ordered pairs on that line, those also describe that relationship. You know, those ordered pairs might be 0, -1, 1, 2, and so on. Okay, so that set of ordered pairs, those x and y values that correspond to each other, those can also demonstrate or kind of give an example and show that relationship between x and y. Then we can also use what's called a mapping. And actually, if we go back to this right here with engine size and gas mileage, this diagram that I drew, this right here, we would call that a mapping. So we have, you know, the x values here and then arrows going to the y values. And these are really the same as saying 260, 25. That could be an ordered pair. Okay, so those arrows just show that 289 and 20, those are linked together, so we could also write that as an ordered pair. And so these are all four different ways of showing the relationship, but they're all very connected. You know, we could take an equation, draw a graph of it, get some ordered pairs from it, and then make a mapping. And it's all the same relationship, just shown in different ways. Here's another example of a mapping. This shows states corresponding to the numbers of representatives in those states. You'll notice, you know, just like that diagram I drew earlier with engine sizes and miles per gallon, we have these arrows showing the correspondence between each state and their number of representatives. And again, I can use that if I wanted to, and I could write a set of ordered pairs. That's what this right here is, with all these braces and parentheses. This is a set of ordered pairs. Notice I've got 6 different ordered pairs here. Typically we think of ordered pairs being 2 numbers, but Alaska 7, that's showing this input value Alaska corresponding to that output value 7. So in parentheses, Alaska, comma 7, that's an ordered pair. Got a whole list of these here, and then you'll notice we've got these braces. Okay, if you see a list of things inside braces like that, you know you're dealing with a set of objects. And we'll talk about set notation and how that works and why that's important when we start talking about domain and range here in just a little bit. But these two, again, are the same relationship, just shown in two different ways. Okay, so we see what relationships are. Let's go ahead and from that, let's define a function. Okay, a function is really just a special type of relation. And here's our definition for that. Here this says a function is a special type of relation in which each input value has only one output value. So what does that mean? Each input has only one output. If you look at this example we just covered with states and numbers of representatives, you see that each input, all these states, don't they have exactly one arrow coming off of each one of those? Each input corresponds to only one output. California corresponds to 53 representatives. California doesn't have 53 and 7. Each input has only one output. Okay, so doesn't matter. Notice that value 7. We do have two. We have two states that both have 7 representatives. That's not a problem. We can have several inputs that all go to the same output. That doesn't violate that definition. What we really want to look at is this left-hand side of this mapping here. Does each input have only one arrow? And that is the case. Something that's not a function, look at this. This is mapping people to their phone numbers. So we've got Dan, Gizmo, Colleen, and Phoebe. All these different phone numbers here. You'll notice Colleen is causing a problem. She has 2 phone numbers. That's a single input going to 2 different output values. So this is actually not a function, because Colleen has 2 phone numbers. So that's what a function is. Each input has only one output. A couple of other examples just to kind of make sure that's clear. You could think about people and their birthdays. Each person has only one birthday. You can't have a person that's physically born on 2 different days. It just doesn't work. Okay, there is a single birthday for each person. So each person has one birthday. That's each input has one output. Okay, let's look at these examples here, and I'll get to these notes up here, a couple more definitions in just a minute, but let's look at these first examples. It says, determine whether each relation represents a function, and for each function state the domain and range. So does this represent a function, this mapping here? And I would say, yeah, it does. Each input has only one arrow, so that is a function. So we could say, yes, that is a function. Now the next part of the question, if it is a function, state the domain and range. So let's go ahead and define domain and range. I mentioned it earlier, but I said we would get to it later. Okay, later is now. So let's look at what is domain and range. And just to easily define that, there's a definition up here. It's a little mathy, a little wordy, just to kind of simplify it. The domain is all your input values for that function. So any input value that's in that function is part of the domain. Okay. So if we wanted to state the domain, we would say that the domain, we're going to list this set of values here. So I'm going to use a curly brace, and I'm just going to abbreviate no high school diploma, some college, and college graduate. So those values there, just listed in curly braces, that states the domain. Okay, well if that's the domain, you can probably guess what the range is going to be. Okay, those values right there that are your output values of that function, those are the range of the function. So again, just listing those The range is 7.7%, 5.9%, 5.4%, and 3.4%. Okay, so there I've completed that. I've got my domain and my range here listed. Again, the domain is always your inputs. The range is always your outputs. Here's another example. First, is that a function? We have calories on the left, grams of fat on the right. Hopefully you can see that each arrow coming off here, we don't have a single value for calories with two arrows coming off of it, so this is a function. To state the domain, remember that's the input values. So I'm just going to list these different calorie values: 410, 580, 540, 750, 600, and 430. For the range, that would be the grams of fat. My marker's going crazy here. Okay, so the range is the grams of fat. So 19, 29, 24, 33, and 23. And I see no good news in that mapping between calories and fat grams. Any way you swing it, I don't think there's a healthy sandwich up there. But that's it. Okay, we do have a function. Each input has one output, and just listing those values in that set notation for the domain and range. Here we have a mapping between carat weights of diamonds, I presume, and their price. First, is this a function? I want you to look. One output, one output. Each of these have one output, but you get down here to the bottom. 0.86 carats has two output values. It's two diamonds, both 0.86 carats, but with two different prices. So this, because of this right here, this input having two outputs, not a function. And here, just following the instructions, it said if it is a function, state the domain and range. Since this is not a function, we're done with it. We don't have to state anything on the domain or range. Okay, so that's mappings. We said there's 4 different ways to show a relation or a function. Mappings is one of them. Here we have 3 different sets of ordered pairs. So we want to ask the same question for each one of these sets of ordered pairs. Is it a function? Okay, so one way to see this is to actually just make a mapping. So for example 4 here, I can make a quick mapping. The ordered pair 1, 4 means that the input value 1 corresponds with the output value 4. Just going across there, I've got 2, 5, 3, 6, and 4, 7. Looks to me like each input has one output. So yes, that is a function. I'm just going to put a check mark by it because it is a function. Stating the domain and range. For the domain, again, domains are input values. Once we see that mapping there, we can see that 1, 2, 3, 4, those are the input values. Plain and simple there. We can look at 4, 5, 6, and 7. Those are the output values, so those are our range. You can also just look at the ordered pairs. Notice all the X values, 1, 2, 3, and 4. Those are our domain. And then the Y values for our range, 4, 5, 6, 7. So you could also get those straight from there. Example 5, is that a function? Looking at those ordered pairs, I have 1, 4. I have 2 also corresponding to 4. Is that okay? Yeah, that's fine. That's an input of 1 going to 4, input of 2 going to 4. Each input has 1 output, even though they're the same output, no problem. 3 goes to 5, and 6 goes to 10. I would say that's a function. No problem there. Quickly stating the domain. My input values are 1, 2, 3, and 6. And then the range, I only have 3 output values here. Even though 4 shows up twice in 2 different ordered pairs, really I just have to list it once. So I can just put 4, 5, and 10. So there's my range. No need to list 4 twice in that set. And then the last one here, you can make a quick mapping, or you could also just notice, by now you may have picked up that you can just kind of pay attention to the x values and see if any of them are repeated. Okay, so -3, -2, 0, 1. Hey, there's -3, which was the same as back there. Do they have the same output value? No, that's a -3 and a 9, and a -3 and an 8. If I were to make a mapping, that part of the diagram would look like this, wouldn't it? -3 going to 9 and to 8. Our other values, just to kind of finish that, would look like this. But really the part that's the kicker for us is -3 corresponding to 2 different output values. That right there tells us this is not a function. So we're done with it. Okay, these next 2 examples say determine if the equations define y as a function of x. So this is a little bit trickier. We can look at a mapping or a set of ordered pairs and pretty easily tell if each input value corresponds to exactly 1 output value. You just look at the arrows and it makes sense. What about an equation? Looking at y equals 2x minus 5, how do we know whether each x value has exactly 1 output value? Each x has exactly 1 y. And it's not really clear at first how we could figure that out. And basically what you need to do is just kind of test out an x value and see what happens with it. Okay, so for example, if I take example 7 here, y equals 2x minus 5, let me just try a couple of x values here. Maybe let's try x equals 1 and see what happens. If I plug in an x value of 1, that means y is 2 times 1 minus 5. And what I'm really concerned with as I try this out is not really what the answer is, but what about the steps along the way? Okay, is there more than one path to get from an x value to a y value? So here, 2 times 1, okay, there's only way you can do 2 times 1. There's only one way to do that. 2 times 1 is 2. And then 2 minus 5 is -3. So from this x value 1, there's really only one path to get to -3. You multiply by 2, you subtract 5, and that's it. And you could try another x value. You're going to find the same thing. As I try that x value out, is there any way I can get 2 different answers for this first step? 2 times 3, there's only one way to do that. 6 minus 5, there's only one way to do that. So it's pretty reasonable to assume that if I start with an x value and do the operation of multiplying by 2 and then subtracting 5, I'm only ever going to get a single y value. There's not 2 different answers for multiplying by 2 and then subtracting by 5. So here we could say that yes, that equation defines y as a function of x. Again, it's a little bit trickier. You kind of have to reason it out a little bit and think, okay, if I plug in an x value, are there 2 different paths or 2 different ways to get to a y value? In this case, there's only one way, so that is a function. Okay. Just ignore what I tried to do there. Example 8. Let's look at one that's a little bit different. X squared plus y squared equals 1. So let me just start with an x value. Maybe x equals 0. Try that out. So 0 squared, actually, let me put that in. Yes. If you square 0, you just get a 0. And then 0 plus anything, well, that just gives you y squared. Okay, so far, squaring a 0, only one way to do that. 0 plus something, there's only one way to do that. Now, this step here, y squared equals 1, now that's a little bit different. If I think about how to solve that, or kind of what y values work here, isn't it true that from this I could get that y equals 1 or negative 1? If you square a 1, 1 times 1 is 1. If I square a negative 1 times negative 1, that's also positive 1. So in other words, here I started with an x value of 0. In the end, I could have two possible y values. X value 0, two possible y values can work there. So in a mapping, that's what this would look like. Well, what does that look like? That looks like that's not a function, right? And so that is the case here, that is not a function. Y is not defined as a function of x. And it's really this y squared that throws a kink in the whole thing. And just as a general rule, 9 times out of 10, I won't say every time, but 9 times out of 10, if you have a y squared in your equation, it's not going to be a function of x. That y squared, squaring that y value, again, that's what really throws a kink in the whole thing. So those are a little bit tougher.